Hi, welcome to the chapter of design methodology in the VLSI course. And we would like to go over some introductory material and the design strategies, methods, flows, and design economics. And we're going to stay um, uh, as much as possible at the definition level because every one of those is really deep topic by itself. Okay, so let's see if we can define what is a design methodology. Um, Pretty much every time any one of those high-tech company performs a project, after the project they examine the process and the flows that they have gone, the steps, and they try to come up with best practices, best strategies, best set of principles, if you will, and all the purpose of that, so that when next time when they do another project, so this is project, for example, I, when they go for project I plus one, they will do it better. So really, design methodology, what they mean, methodologies are really strategies, right? That are sort of um, derived from past experience, and the purpose is to increase the likelihood of success. So to put it in a simple example, suppose you commute from point A to point B, and let's just say the road is not straightforward. You have to go through lots of detours and uneasy routes. And then next time you go, you find out a better way to do it, and then the third time and the fourth time. So every time you go through it, you really learn a better way to do things, and this is to increase your likelihood of success. Okay, that's basically design methodologies. Okay. Now, integrated circuits can be described by three domains, or I would say views. Okay, views. There's an E here, and those views or domains describe the design from different perspective. So you have the behavioral view or domain, which talks about what the design do, the what is it intended to accomplish. Then you have the structural view, which talks about the interconnects of the components. And you have the physical view, which talks about the arrangement of the components and the physical components. Now, and obviously, these views, if I may describe it in the analogy, um, when we were when we took the design um, drawing. Let me go to the whiteboard here. When we had our oops um, when we have our drawing engineering drawing class, we used to have, for example, a house, and then we uh, they give us the front view and the side view and the top view, and then they used to ask us to draw in the cross section of the house, for instance. These are different views. They show you the same thing, but from a different perspective with an emphasis on something. Okay, and this is exactly what we are talking here about in terms of the views or domains for which we are describing the devices. Okay, now uh, uh, along with the views, we have different design levels. When we start describing a design, we describe it at the architectural level, and then we design down to the logic level, and then we design down to the circuit level and the transistor level. You can combine these views in this Y chart this chart basically explain or integrates the views in these axes and the levels in these circles. Okay, you can see this. So in the outside, when we start the project, we describe the behavioral view at the architectural level, and we try to think of what we need in terms of interconnected components and interconnection, the processor, etc., and then what type of physical components, boards, and systems. Then we move to more detail to the RTL, okay, and logic, and where we talk about in terms of the behavior view, we'll talk about the algorithms, the some of the OS, the applications, and here in the structure we start to talking ALUs, registers, modules, and here in the physical modules as well. And then we go deeper, moving from the architecture to the RTL to the circuit level, obviously as it's stated here in the earlier slide. So these are, and in every level of those, we're going to describe things with these views, the behavioral, the structural, and the physical. And those views help to give a complete, comprehensive view of the design. Okay. Now, obviously, a very good VLSI design, as states here, it has to be consistent on all these views or domains. In other words, if we have something described in a behavioral level or behavioral domain or view, and then we transform this design and we express it in the structural level, we better make sure that this is the same as this. If there is a mismatch, if there is a design difference, then we are not expressing the same thing. And even when we go deeper from architecture to logic to circuit, we have to, as we go deeper on those levels, we have to make sure that this transformation is correct, and all these views and levels represent the very same thing. So we have to do lots of testing and verification. Okay, so it's important as we design and represent the design with these different views to keep our eye on the performance, the size, the time to design, the ease of verification, and the list goes on and on. And obviously nowadays there is a very strong emphasis on power and energy. Okay. And so this is should be added to the list. Okay, so obviously there are trade-offs. In other words, for example, if you increase the performance, typically that will be on the expense of design, power, and energy. You need you need to have more energy and power. Okay, of course we have design aids to reduce the complexity and increase productivity, and these typically comes in terms of tools and expertise in the area. Okay. So now we talked about the definition of the design methodologies and how we represent the design with different views at different levels, and we need to keep our eye on the performance. Let's now talk about the design principles. And these design principles, quite frankly, apply to both hardware and software. And in other words, they are really taught in both hardware classes and software classes, and I teach them in other courses as well in great depth. These are important design principles, and uh, you will see they will use appropriate examples in the software courses and appropriate examples in the hardware courses, but really the overall principle apply whether you are designing a hardware or a software. So what are these design principles? Hierarchy means what? It means really if you have a large design. Okay, like for example, he's given you here, you have a software radio microprocessor. And this is a large design. If you try to design all at once, then the task becomes complicated, time consuming, and the failure rate is really pretty much high. And what you really need to do is to divide this into smaller, what we call in hardware modules, what we call in software classes or subroutines, okay? So that these are manageable pieces of design, whether hardware or software. So basically, what we have here in terms of hierarchy, we need to divide and conquer. We really divide the system into smaller, manageable, comprehensible modules or pieces of design. Um, so the best way, once you split your design into these modules, you start verifying those at the bottom, and then you go up. So for example, if you have your design split like so, so you would want to verify these components at the bottom, the smaller components, and then you go to the ones that instantiate them, and then the one on the top. In fact, if you verify those components, typically their verification and testing is easy, and then the upper ones becomes more of a simpler verification, and the focus will be in connectivity because you have done good job and functionality at those leaf modules. Okay, so you would want really to start from the bottom to the top, and that should facilitate your hardware, your verification. Now, assume one of the hardware is not ready out of those. Suppose this is not ready yet, and you wanted to do verification, continue the design. You can really use what they call here a soft version of this, and plug it in here until the design is ready. So let's suppose, for example, you have a bus, and say this is a new USB bus, and you want some other company is designing this for you, and you're buying the IP from them, but they don't have the design ready for you. What they could do, they supply you a software version of the IP, so you can do your simulation and verification and design process and continue with it until the full complete design is delivered to you. Okay, and that's the benefit of having modules, because if you don't have to split it on that level of modules, you wouldn't be able to plug in a small piece of software for that module in your entire hierarchy. Okay, the other principle is regularity. And regularity basically means is that I try to divide my design into a set of similar building blocks, and the reason is, why would you do that? And for two main reasons. First of all, if you can, so let's give an example. Suppose I did my job of hierarchy without a regularity, and I did the hierarchy, and I wasn't careful with regularity, and I created about, let's say, 50 small modules. Okay, and then I re-examined these modules, and I was able to create, or repartition my design into with a smart way, into four modules that are used repeatedly, like for example CPU, RAM, for example, arbiter, okay, DMA, for example, and these are used repeatedly, and then I have, for example, 10 other different ones that I need to, they have to need to be different. No, now notice the two situation here. I have 50 different ones that I have to design and test, versus here I have 14 versus to design and test. So notice every one of those I need to design once and use many. So that's design reuse, and that will save a lot in my verification process and design process, because since I will have to design and and verify those guys once, that tend to save my time. But I have to apply this principle of regularity, and I have to find where are those similar blocks and identify them. Okay, so regularity creates for me data path modules, uh, regular arrays, etc. This is in the hardware. In the software, this belongs, or this is similar to when we use iterations on code sharing in software. Okay, because we identify those similar codes, similar designs. Okay, an iteration is basically you iterate the loop, and this loop is used again and again and again in that for loop or while loop. Okay, another design principle is modularity. And modularity, what it means is that you really define an interface for your module. This is I've decided to have a module where I have it does certain function here. Okay, I have to define an interface for it. That interface, it makes it easy to integrate this module with other modules, right? Whether this piece is software or hardware, doesn't matter. In hardware, the modularity really belongs to the input-output ports of the module and the timing data for the input and output. And this is really important, as I said, when we integrate this with other modules and try to hook it with other modules. I give always this example that suppose for electricity plug, and we have lots of conventions of these electricity plugs. Okay, whenever you try to hook your electricity plug, this is your device here. Okay, and this is the electricity plug, and notice this is the interface. If this is well defined with the electrical plug in the wall, so you can plug this right away because the interface is well defined, because the interface matches whatever the plug with the plug in the wall. It makes turning on the device easy. So that's a very simple example of a clean, well-defined interface. Similarly, we have over here. Okay, so the ability to divide a task into a set of well-defined modules also aids system on a chip design where the number of IPs to be interfaced to be interfaced to a complete design. Okay, so basically the interface, one more time, it helps to integrate the modules at when we start connecting them, and the more this is defined and clearly defined by the name, by the signal type, by the electron, by the time, the cleaner this integration becomes. Okay, one of the most common mistakes in hardware verification is that you will see that people will hook up hardware pieces with probably the same signals, but these signals could mean something different, slightly different than each other, and this create a hardware bug because of this definition of this interface is not accurately described. Okay, in one of the interfaces. Now, locality. It really means that we hide the internal details of the module. It is all about hiding the details of locality. In software, if you have, like for example, a class, if you have a private member, you, the outside world doesn't need to know about it and should be hidden from the outside world. In hardware, it means that you describe all your timing to a clock inside your block. You don't reference outside the module, and so you keep the details internal. Okay, if you have signals that are inside your block, you don't expose them to the interface. So, for example, if you have something like this uh, type of logic, and you have this signal, so this node does not need to be in the part of the interface, and so is this one. they only need to be visible at this output node. So these are local nodes. Their layout, their electrical properties, the capacitance, everything should be local to inside this module, because you want to hide the details from the outside world, because it doesn't need to be exposed to the outside world. And now we can see that these design principles, hierarchy, regularity, modularity, locality, really applies to both software and hardware, as I mentioned earlier. So hierarchy means creating modules, splitting your top design into modules, and then connecting them at the appropriate way. Regularity, identify data paths, like for example adders, multipliers, small ALUs, regular array, so that you can promote reuse. Modularity, you have to think of the interface, very accurate, well-defined interface. And locality, really anything local, you keep it inside your design. It doesn't need to be exposed to the outside world. And now, with that, we are ready to look at, after the design principles, the question is, what are the design methods? So a common question for students is that when it comes to hardware, and actually this arises typically in the senior design project, the graduation project, and they typically the students have their design project, and their question is, what is uh, uh, the platform, the method that I should design? Should I use CPU, Arduino based board? Should I go for FPGA? Should I? So what's the appropriate method? So there are different methods, and let's just go over them very quickly. One of them is the microprocessor DSP method, and this is basically when your solution for the problem is mainly software. You write the code in assembly, in C, in C++, whatever you want, and then you let the microprocessor execute that code, or the digital signal processor execute that. And there are many examples of that, of this family. So your solution basically becomes mostly software. The other way you can do is programmable logic. Those you kind of download or configure the hardware with your solution, and with that you can think of logic array, programmable logic array, and they are efficient, with the certain limitations, and they are good as well. They are better than the microprocessor and DSP. They are typically faster, okay, and provide good solution for small problems. And then you can think of, in this category, the FPGAs. You can write your solution, describe it in a language like Verilog or VHDL. I think we did that already in the internal lab, and then download the hardware into the FPGA. Altera, Xilinx, some of the examples of FPGAs are out there. Okay, and then we can move into the cell-based design, where basically you buy a library of cells, and then you take your code, okay, and synthesize it, and the synthesized code will use these library of cells. Okay, of course you will need a placement and route tool so that you can place and route these cells. So that's another solution. And then the final is the full custom, and the full custom is the most optimum solution in terms of speed and power, but the most expensive. In fact, it is so expensive that many companies are going away, reducing the full custom design as much as possible, because it's really very costly. So, and then you have the platform, where you have a system on a chip. And basically, this is when you have really in your system. Typically, some of those FPGAs and other hardware platforms, they provide for you a microprocessor as a host, a bus structure, a memory, and you just need to stick in your solution, hardware or software, in that system. So they provide the backbone of a system for use. This is called the platform-based solution. Now, if we go and compare these solutions, these solutions vary based on their cost. Non-reoccurring is the cost, really cost to design the first copy. Okay, the first design. And unit cost is that when you design the first copy, then you want to make the next 1,000 or 1,000, you need just the cost of the material and the testing. Okay, and then the power dissipation. Okay, um, the complexity of the implementation, time to market, performance, and flexibility. Notice overall, if you look at the microprocessor and DSP, which is a software solution, this is where software solutions and we go more hardware like so. Notice that the design goes, the design cost, the non-recurring engineering cost goes higher whenever you go to more hardware solutions. Okay, but the unit cost increases whenever you go to software solutions, because hardware solutions tend to, if you do them very carefully, tend to be optimized in terms of the cost. Power, it is more towards the software solutions, excuse me, and hardware complexity, more towards the hardware solutions. Time to market, how much time we need. More hardware solutions takes lots of time. Performance, hardware solutions are better. Okay, how about flexibility? Well, typically programming solutions are more flexible. For example, for instance, if I make a mistake in my code, which is I'm writing on a microprocessor, well, I can just fix the code and compile and run again. But if I do a mistake in my custom design, well, the flexibility is very hard. Basically, whatever I manufactured, I have to throw it away and redesign and manufacture again. So the flexibility is high for the microprocessor and the FPGA because of their programmability. Okay, you can see the trade-offs between all these methods. Typically, power and performance, they just kind of opposite to each other. So we would like to have low power, but typically that ends up with low performance. Okay, uh, it is important um, to realize that. But in this case, okay, so as I said, typically if you improve the performance, you have high power. But in this case, because we are comparing families, we see across the family the custom design provide for you a very high performance with low power. Okay, but within the custom family, typically the circuit, if you vary them individually, if you improve the speed, typically that comes with higher power. But those families, when you compare them, the software solution families, they have low performance and higher power dissipation. Okay, so this is kind of a comparison between these design methods that we can implement our or use to implement our designs. Those designs can be our graduation project, it can be our IP, it can be our solution in our company. Okay, so these are the available design methods. Okay, so now we talk about design flow. And a flow, the concept of flow means steps, collection of steps. And obviously, you have a first step and a final step. So the flow describes the steps from a product requirement or specification all the way to manufacturing that product. This is called the flow. And obviously it starts with those steps that has to do with the behavior, and then the specification and the physical views. It's important to know that even at the early steps, while we emphasize more of the behavior, we do talk there about these early steps about the physical and the physical domain and the structure. It's not that we ignore this completely, but the emphasis is more on the behavior, the behavioral function, functional specification, and then we go the behavioral RTL. We do the synthesis, then we do the structural specification, the physical synthesis, and the physical specification, and then we end up with the tape out. Obviously, there has to be what? There has to be a check, verification test, because we are doing a transformation. Anytime you do transformation, you need to cross-check the two end of the transformation, because if you don't cross-check, there might be a bug or an error in the design and you are not aware of it. So you have to do that verification every step of the way. Okay, now design economics, Moore's law told us that every 18 months, we double number of transistors in an IC. Now, by the way, this has slowed down nowadays. People nowadays have made this 18 months to 2 years, and with the sort of people now talking 5 nanometer technology and lower, it is becoming harder. Of course, yeah, the 10 nano people are actively working on it, but the 5 nano and lower technologies becoming uh, very sophisticated, more expensive to uh, build those fabs and equip them with these sophisticated technologies. So, uh, yes, this Moore's law is still ticking, but it has slowed down. Um, uh, of course, people since long time they mentioning that we have hit the physical limits, meaning we no more can shrink transistors. Through the process of shrinking transistor has slowed down. Dynamic power is high, so, leakage is high, short channel effects is hurting the design, fabrication cost is to the roof, electromigration when you have the metal fuses because of atoms are displaced and causes disconnect and this interconnect delay. But you know what? This all exaggerated every time we manage to find solutions in every node of the technology. So there is a bit of exaggeration, good for hype up for people to work on on the solutions for the next generations. Okay. uh, VLSI economics, we can't ignore them as long we are talking strategies here and methodologies. Economics says that if you have a selling price, then how do I set it? Well, you calculate your cost total. Oops. You calculate your cost, total cost. And there again, I did it again. This is C total. Okay, and you divide 1 minus margin, and the margin is the profit margin. This becomes your total, this becomes your selling price. This is how you compute your selling price. So for example, if you for example manufactured a part and it costs you, for example, $10, right? And you want a profit margin of 20%. So this becomes one, oops, again, this is happening. 1 minus zero point 0.2, okay? And this becomes your selling price, okay? So then the question is, okay, now I know the selling price. So I calculate the C total. Well, the C total includes non-recurring engineering cost, which is the cost of making the very first design. And second, recurring cost, which is the cost, the material cost, the testing cost of every other copy, and the fixed cost, advertisement, and all that stuff. Okay, so let's talk about the NRA, non-recurring engineering cost, and this means R&D. It is we need to design, we need to find out the very first copy. We need to make the very first design, and then we can copy it. Okay, to make that, well, you have to go through engineering costs. You have to hire engineers. Okay, and this there will be a team of a size of 10 and 20 or 100 or 1000. You have to provide salaries, training, computers to them. You have to provide software tools for these expensive software tools. Some of them, they run in the millions in terms of licenses. And after that, you will need to create a prototype. So your first design has to go through prototype manufacturing. This is as well part of research and development, which is the non-recurring engineering, because it happens once almost in the first copy. Now, once you make the first copy, then there is the recurring cost, which means the cost of making every other design thereafter. So that include the process cost, the packaged cost, the test cost. Okay, so because you need to test every part, you need to have a cost for the package, and you need to manufacture every die. And the process, we can say it is the wafer cost, divide this by number of dice and divide this by the yield, and the yield can be the multiplication of the die yield by the package yield. Okay, so that's how I did. So the cost of the process, it is the wafer cost divide by dice per wafer times the yield. So what's dice per wafer? Dice, how do I compute this? Well, this is an interesting math problem actually, because the wafer is circular almost, and then you have these dice or die. They are sort of like a square type, sort of like uh, uh, rectangle. So, but let's assume they are square. So the question: how many complete squares you can squeeze in this circle? Okay, so this becomes the question: how many squares? So people thought about this and came up with all interesting formula. Assume the radius for this the circle is r. So the distance from here to here. Okay, this is 2r. This is um, this is 2r. Okay, so from here to so the radius is r, and assume that the side of this square is a. So what people found out is that the number of squares, complete squares in this circuit is equal. You divide the area of the circuit over the area of the square. Then they found people that this is very optimistic. Then we have to have some correction term. So they will say minus the diameter of the circle divide by this side of, okay, which is the diagonal side here of 2a, square root of 2a. Okay. Now, in this example, because of the square happens to be equal to diameter, not a good drawing that I'm offering here, by the way, because it's perfectly for. But anyway, so you get the idea. This is uh, let's see if I can get a drawing here, a better drawing. Okay, so if I have here a circle. Okay, and this is the radius for the circle, and then I start making those squares. Okay, those squares, try to fit those squares, as many of those squares as I can. Okay, so now this is a, the side is a of the square, and this is the square root of 2a. Okay, and this is the circumference of the circle, which is equal to 2 pi r, and the area of the circle is pi r squared. So the expression says that to find out the number of complete squares, you have to divide the area of the circle by the area, okay, of the and notice in your notes, he's taking the pi expression as a common factor uh, by the area of the of the area of the of the square. Now the area of the square is a, so this ought to be square root of a. Okay, correction from me here. So this is a square root of a. The length of the side of the square is square root of a. So the area becomes square root of a times square root of a and becomes a minus the circumference of the circle, which is 2 pi, or divide by the length of the diagonal here is square root of 2a. And in your textbook, what they did, they took the pi outside, okay, as a common factor. That's the formula basically that you have in your textbook. Okay. All right. So and the yield here, which is the package and the die, we can approximate as y raised to the e minus a. This is the area. This is the area, uh, uh, and of the design, or the die in this case, and the d is defect per centimeter square. Okay, the defect. And this also makes sense that as when the area increases, then your yield becomes zero. This is because when you have large die, any error in one of those dies will deem that die defective, not useful. But when you have small dies, any error, one error that comes in one die, any design defect, it will impact that little die alone. Okay, so as the area goes small, then the yield approaches 1. Okay, fixed cost, which is the third category of cost. This includes advertising, marketing, application notes, data sheets, etc. And here's an example that says that if the defect density is 0.4 defect per square centimeter, okay, that's the D right here, okay, and what is the yield at this area? This is the area. So YW equals E minus 0.4 defect over square centimeter, okay, times 1 square centimeter. Okay, if this cancels this, and this becomes E minus 0.4, and this is 0.67%. Well, what happens if the chip area grows this much? So Y equals, this is the yield of the die, E minus AD, which is equals to, let's, sorry. Okay, so this equals 0.4 defect per square centimeter times 5.75 square centimeter. Okay, so we cancel this with this, and then we do the multiplication here and raise it to the e. Notice the negative sign here, and that comes into 10%. Okay. All right, I think with this example, we conclude our discussion for the VLSI methodology chapter. Thank you very much.